Assalamualaikum warahmatullahi wabarakatuh. So today for SFG4093 Nuclear Physics for lecture 4, I provide this video for those who can attend for our lecture, physical lecture for face to face. So this will cover topics that we will discuss for today's lecture. So before this, we have discussed a lot about the basic structure of the nuclear itself. We're still in the part of the nuclear properties and also the strong force. Last week about the strong force. So for this week, I still cover a little bit about the nuclear properties, which is the size and also binding energy. Okay. Because it will help you, especially for the tutorial. Before we can go for the next topic about the nuclear model. So this is the graph of the electron scattering on the nuclei for the oxygen and also the carbon. So this is the experiment they've done using the electron scattering. Okay. So they get the value of the energy then, and this is the nuclear of the charge distribution. So this is what we need to know about the nucleus from this graph, and from there we know that the boundary of the nucleus is not sharp. It's not the like wall is very sharp, but its display probability distribution means that they have a something like wave. The angular distribution from scattering of the electron from nuclei do not show sharp minima, so this minima become less sharp with the increasing of the Z. And the central nuclear charge density is nearly the same for all nuclei. Okay, the central nuclear charge density nuclei basically same for the all nuclei, so it's not depend on the density of a charge as a function of Z. So the nucleon also, which is proton and or neutron, do not seem to perfectly organized based on the type. So it's not arranged in the nucleus. It's not arranged like a proton, neutron, proton, neutrons, or proton, proton, proton. Neutrons is not something like that. It's mixture. So the overall matter density of the nucleon in the nucleus must therefore be constant as well. So first, discuss about the density of the nuclear matter. So density, the basic density, we know that mass versus mass over volume. So in the basic density means that ketepatan in Malay. So we have a certain box or square, anything. Okay, they have size or the volume itself, and then how many things inside that, so that become the density. So if the mass increase, means that they have a lot of things inside that, so the density will increase if we have the same volume. So if the mass reduce, then the density will reduce. But if the vessel itself, the volume itself reduce, then the density will increase in the constant of the mass. But if the volume of the example square or everything sphere increase, then the density will decrease. So they have made assumption that the nucleus is in the perfect sphere. From then we can estimate the volume and perhaps the density. So the volume for the square, the sphere is 4/3 pi r3, which is r is a radius. So the nucleus itself contain proton and neutron that mixture inside them. So if the nuclear matter density is also indeed constant for all nuclei, okay? So means that the velocity of the volume itself is constant. So we can relate the radius of the nucleus to the number of the nucleon. So they have a relation between the radius and the number of the nucleons. So that means that A is a total between proton and also the neutron. So when we try to determine the proportionality constant, so we can relate the total nuclear matter radius to the matter radius of the individual nucleons. So the nucleon itself can also be considered spherical. Okay, We not discuss detail on the nucleon inside the nucleon, which is proton and neutron that built from the quarks. So we not go deep on that. So they have assumption that proton is a sphere and neutron so then spherical. So therefore, so we create the new correlation here so that we can get the radius equal to R naught E 1/3. So from the experimental, we know that the R naught, the radius, okay, which is 1.2 femtometer. So the nuclear matter radius is the R times equal to 1.2 A power of 1/3. Okay. So it's the nuclear matter radius, the whole radius. So we need to know what happened to the volume itself, okay, the density. So you can see that they have several density that we can measure that or compare, okay. So it depends. For example, seawater we have a density of 1 times 10 power of 3 kilogram per meter. Thin oxide, core of the sun also 1.5. But for the nuclear matter itself, it's 2.3 times 10 power of 17, which is very dense. Okay, density very high inside the nucleus. Okay, the dense matter. Some interesting part, it will be the neutron star itself. Okay, this is part of the poster from the Nature. That something interesting that you can refer here. So the neutron star also we have is a dense matter. Okay, here they have a correlate between the quarks. So we will discuss more on this standard model. Okay, next is about the nuclear binding energy. For the previous lecture, we have discussed basic calculation on the nuclear binding energy. But for more details on the nuclear binding energy, they have another things that can help we understand the bunch of the nuclei that can be correlate between each other. That finally we can conclude which one is a fusion and fission reaction. Okay, spontaneous reaction that can get. So first of all, before we can calculate the nuclear binding energy, we need to calculate the mass defect or the excess mass, because we know that one nucleus, okay, example contain, example for helium, we cannot put hydrogen because hydrogen only have one proton. Example helium, or any so the any matter they have a number of proton and number of neutron. So number of proton, proton have a mass, neutron have a mass. When we total up the mass, we have a certain value, which is we assume that the total mass of the nucleus. But from the experiment, when they measured the mass, the mass actually different with the calculated mass. So there's when we differentiate between this difference between these two mass, that what we call as a mass defect or mass excess. So that mass actually we bring together will become the nuclear binding energy, because the extra mass that actually create the energy that become a binding between the proton and neutron. So here actually split into two. There's a pointer here. Okay, so this one section between ZMP plus and N, which is Z is a number of proton times the mass of proton. So if you have two proton, then 2 times the mass of proton. And then for plus number of neutron, so you have number of neutron, or if you can get A minus Z, okay, number of atom minus mass of atom minus the number of atoms, then we can get the number of neutron times the mass of the neutron. So we can get this mass of the nucleus for the theoretical minus the mass from the experiment. So they can get the value of the mass defect. So this is mass of the nucleons. Okay, mass of the proton and neutron inside the nucleus but the atomic mass is a bit different. So from here, from the excess mass, okay, the mass defect, we can convert this into the energy. So using the E equal to mc square, which is the delta M here. And to calculate it, we know that one atomic unit, because in here mass, calculate using the atomic unit, and we try to get the change to the energy. So energy we are using the mega electron volt. So from there, one atomic unit, we know that equal to 931.5. We have discussed before, mega electron volt over c square. C square is the speed of light. And then we rearrange here, we can bring the speed of light here. So means that c square is equal to 931.5 mega electron volt over one atomic unit, for one atomic unit. So we can bring here c square 931.5 times the mass defect. Then we can get the binding energy. Okay, here, yeah. Oh, sorry, here, binding energy. So now you know one nucleus or nucleus have the proton and neutron, and then different between the atomic mass and the nuclear mass, and then the mass excess or the mass defect there, you calculate to get the binding energy. The energy that we call as binding energy. Okay, energy that bound the nucleon. So they have something we call as a binding energy over nucleon. Means that nucleus have two proton and two neutron. So the binding energy will divide over numbers of the nucleon itself. So why the binding energy over nucleon important, and we will discuss later. But keep in mind, the binding energy, we cannot compare only by the binding energy, because when the number of the nucleon increase, and of course the binding energy will increase. But dot you present the what happened inside the nucleus itself. Okay, they have another two energy that we discuss, which is neutron separation, also the proton separation. So nucleon separation happen because amount of energy needed to remove the neutron from the nucleus. That's why I call this for the proton separation, to remove the proton. So that's what happen when you have the isotopes. Okay, now we back to the binding energy over A, over the number of the nucleon. Okay, so we know that the binding energy is the energy needed to break the nucleus. Okay. But from the calculation, like we discussed before, when we calculate the binding energy, we know that oxygen for the 16O, we have binding energy 128 mega electron volt, and for uranium 225, they have massive binding energy, which is 1700. Okay, so 1786 mega electron volt. From here, what we understand actually, uranium have massive binding energy, means we need a lot of energy to remove any proton or neutron from the uranium. Means that uranium must be more stable compared to oxygen. Is it correct? Well, I believe everyone knows that uranium is not stable because you can hit the same thing, then you can create relativity from them. So it's not just too stable, something like this. So we have something because when we compare like this, it's not fair because oxygen only have 16 nucleon inside there. So of course they have a small number of the binding energy, because it bind between the 16 nucleon only, proton and neutron. But for uranium, they have 235 numbers of the nucleon inside. Massive number of nucleon. Of course, they have a lot of binding energy. So that's why to compare between these two nuclei, we need to use the binding energy over A, which is energy over the number of the nucleon. Then what happened? We know that the energy to break one nucleon. So that way we can compare between oxygen and uranium. So what happened? For 1 to 8 megaliter volt, divide by 16, so we can get numbers. Okay, you can calculate. And for the uranium, 1786 over the number of the nucleon 235. So what will happen? The energy needed to break one nucleon in oxygen, we need 8 megaliter volt, but for uranium is 7.6 megaliter volt. It's not too far between this, but we can see that for uranium, we need less energy to remove the neutron or proton inside the uranium compared to the oxygen. So from here, actually, we have something different point of view. Even though they have massive binding energy, but it's because they have a lot of number of the nucleon. Right? So that's why they have a graph that we discussed about the BE over A. I believe that we have learned before last week lecture, but I need to touch again about this. So this is graph between the mass number or number of nucleon. Number of nucleon means that number of proton plus number of the neutron. And of course, number increasing because of the depend on the remember periodic table. So it starts from hydrogen, helium, lithium, okay, and combine until they have a uranium at the end, right? Because this is in the number of the mass number, right? So this is versus the binding energy per nucleon or PE over A. So it's not binding energy but binding energy per nucleon. So from here, so you can see that binding energy for over nucleon increase sharply when we measure the A, okay, from 0 to around 56 or 60 here. Before that, they will increase dramatically, okay, but slowly reducing after a certain point of A, okay. Certain point of the nucleon will start plateau, but after that they will reduce a little bit. So what happened here means that for hydrogen we need very less binding energy per nucleon to remove, but when we increase until the ferrum, okay, this is more stable, high binding energy per nucleon, but actually they reduce a little bit to the uranium here. So this is have a sharp increment here. So the question is why? Why they have something like this? This is what we call because nuclear force is a short range. So how to explain this? Because the nuclear force is a short range, and how this graph actually represent the nuclear force, the short range of the nuclear force. It's a strong force, but it's a short range. So example, one of the, okay, we took this, the first one here, they have 3 nucleon. Example, this is just example. Okay, 3 nucleon. So we have it's not which one proton, neutron, no. Okay, example, we measure this center of nucleon center inside the nucleus. So of course it will affect if these 2 blue particle. Okay, so this nuclear force binding between 3 nucleon. So they have a binding energy over 3, of course. Yeah, binding energy we doesn't need to have a lot of binding energy to remove here. But then the second nucleus here, they have 5 nucleon. This is just example, okay. So at the center, actually it affected or bound with the another 4 here. So it's very strong here. And we go to the another thing. This one have a 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 nucleon, and also they have bound with the 8 here outside here. So the surrounding with the 8 numbers of the nucleon, and of course very strong. But when we go for this one, they have extra number of the nucleon here. The problem here for this actually only the neighbors particle that affect they have the very strong force, not the outside. So that's why at a certain stage here, the number of the binding energy per nucleon become a constant. Okay, and when we reach here, means that it should be similar to this. These three should be have a nearly similar number of the nuclear force or binding energy per nucleon, because the nucleon actually have the nuclear force for the immediate neighbor only. But for this, they have very massive number of the nuclear force compared to the second one. But when reach this one, it become the stabilized. Okay, so this goes to the stability. So that's why in the center here, ferrum is more stable nucleus. Okay, this region. So now we know that the increment because of the numbers of nucleon increase. Okay, but at a certain stage, even though they will increase the nucleon, it's not affect the binding energy because of the force, because they have nucleon that have outer of the space here that not affect or doesn't have, we can call the surface nucleus that doesn't have too much neighbor. Okay, neighbor means that they have reduced the number of the binding energy here. Then come the question, after they stabilized here, around here, it's still when the number of the nucleon, okay, mass number, nucleon increase again and again, but suddenly it reduce the binding energy per nucleon. So what will happen? Why not it's become a constant or plateau? So what happened because of the structure in the center? So they have a nucleus outside, the outer nucleus outside. So this have the what we call as a proton-proton repulsive force that effect. Okay, so that's why they can easier to pull a particle apart. So what happened for the small nuclei? For the smaller nuclei, the binding energy is much bigger than the repulsive force. So it means that the proton will bond with another proton with the help of the neutron. So the repulsive force doesn't have enough force, okay, to pull everything. But when the nucleus become bigger, the outside of the nucleus itself, the outer layer, okay, of course they have less binding energy because it doesn't have too much neighbor compared to the center. So they have the repulsive force. So that will be reduce the binding energy. So that create a border here because on the right side here, we call as a nuclear fission, but for the left side we call a nuclear fusion. So nuclear fission means that the larger or the bigger or the heavier nucleus will break down to become a small nuclei. Okay, so they try to split down. So they are split into small nuclei to be more stable. Toward the stable in the center here. So they're moving to the left toward the stable nucleus. Okay. And then for the smaller nuclei here, nuclear fusion. For nuclear fusion, like element fuse together to form a bigger nucleus. So they merge, you can call merge, okay, fuse together. So it create another heavy nuclei compared to the earlier. Okay, from the smaller cake in a little bit bigger nuclei. So that will be more stable. So everything actually toward the stable nucleus. Okay, creating so we know that fission nuclear reactor, okay, nuclear bombs came from the fission, create a lot of energy from the splitting of the heavier nucleus. So they hit the neutrino to create unstable isotopes. Okay, then that will create that will be discussed later. And then for fusion, actually happen to the for our sun. Okay, they create the helium there and hydrogen. So they have what we call as the value of stability. When there's stable element in the center, okay, we have no something that non-territory, but they have some side of the neutron side that we not really understood. Okay, so we doesn't know which one is the deep line lies. Okay, so for this more proton, actually nuclei with excess neutron move down the value toward the stability. So that will be understanding. So this is a number of the nucleus type that have actually okay, this more clear compared to before this, which is a number of them. We have hydrogen, deuterium, tritium, lithium, we have boron, nitrogen, we have copper here, zinc, uranium, plutonium, thorium, gold, iridium. So this is the number of the type of the element. Yep. So this is another point for the binding energy and the nuclear potential. So our definition of the nuclear binding was correct, but let's make it bit more complete. So a nucleus is bound if number of protons Z and number of neutrino N are confined within their respective potential well. So there's a quantum there you need to understand. So each nucleon must have a negative potential energy. That's why you can get the positive binding energy. Okay, negative potential energy to create the positive binding energy. So the energies of the individual nucleon binding vary dynamically depending on the structure of the specific nucleus. Okay. So means that it's not fixed the binding energy, okay, nucleon binding, because it depends on the structure itself. Okay. So that's why we need to discuss about more for the nuclear shell model or different type of the model. Right. So at this point, quantities such as the proton and neutron separation, SP and SM, become very important. Okay. So we obtain the both value to measurement of the atomic mass. So now they come the question, how do we measure the mass and why do we care? Because they have something that experiment, we must know that they have some experiment or setup to measure the atomic mass. So this is experimental nuclear physics, okay, for measuring the mass. So for experimental must have the quantity, okay, must have the uncertainty associated with them because it's very small. It's not possible to measure something infinite precision. No, they have the uncertainty because we affect something, then it changes another thing. So if they have the uncertainty to get the range of that. It's because we cannot measure specifically because of our weaknesses. Okay, okay. So we cannot get something with precise, but we can get the prediction on that. So it means that we are not directly observing the quantity we want, but rather some interaction that can tell us about the quantity. So that happens when we measure the speed of light. We cannot measure directly the speed of light because our measurement tool is also using the light. So they have some what we call this. I'm not sure. I not think it's a paradox, but it's something that school of thought we try to measure. So usually we try to measure the observe the interaction. Yeah? We have create some interaction, then we try to measure it. We cannot measure it directly. Example, speed of light, we measure from one point to another point straight away. No. Okay, they have some argument there. So sometimes confusing to discuss that. Yes, we cannot measure directly. So same here to the experimental nuclear physics, especially for the level of particle. Okay, so this method can sometimes be model dependent, so which make them unreliable. So at very least decrease their measurement precision. So because the model depend on the uncertainty. So indirect measurement are only used if direct method not possible. Okay. So that's why they have or have other obstacle that cause the large uncertainties. So that's why more in using the indirect method. So when discuss about the experimental, several different measurement technique can be used to obtain the same quantities. So when looking through the experimental data, we aware that what method they use to obtain that. So of course they affect the data. Okay. Often, but older measurement are replaced with better, more accurate measurement. So make sure what you are looking is the most recent data. Okay, that will be remark. Okay, because of the improvement of the tools or measurement or apparatus. Okay, the arrangement of the experimental, so you can measure more accurate. Okay. So that's why physics, especially for the nuclear physics, also need to have large quantity of data to provide input. Okay, so they can reduce the uncertainty then. Okay, this is several method. Okay, using to measure the nucleus. For they have a magnetic spectrograph, time of flight technique, ion trap, and they have another reaction Q value measurement, and also the accelerator mass spectrometry. So I think that will be your task to find out what is this and how it's helped to understand the measurement of the structure. Okay. So there come question, why do we need to measure the atomic mass? Because the atomic mass or the atomic nuclear mass is one of the fundamental properties of the nucleus. It's not the fundamental properties of the particle, but the fundamental property of the nucleus. So it does not change if the environment become extreme. So this is very important because it's not change the nucleus. So from this, we can deduce several important quantities from what we have discussed before, like binding energy, and then we can find the neutron and photon separation energies. And it can apply in the several science requirement, the atomic mass, chemistry also, even pharmaceutical, biology, okay, chemical. Alright, so that's all. So hope that you can get the idea before you can go to the type of model, and hopefully this will help you to understand more about this, and it can help you to do the tutorial that I've given to you. Okay, so thank you very much. Assalamualaikum warahmatullahi wabarakatuh.